Hi, welcome to Algebra 2, Lesson 4-2, Graphing Rational Functions. In this lesson, we'll be able to graph rational functions. The new vocabulary words we're going to see are rational expression and rational function. Let's start with explore and reason. Look at the three functions shown. F of x equals x minus 1, g of x is x minus 1 over 2, h of x is x minus 1 over x minus 2. We're going to graph each function and determine which of the functions are linear, find the y-intercept of each function and the slope if appropriate. So if you have a technology, you can graph it really easily, but if you don't, you also need to know how to graph it by hand. F of x and g of x are pretty easy, but h of x is a rational function that you'll have to plot it one by one. So if you look at f of x, you'll easily see that this is a linear function with a slope of 1 and y-intercept of -1. So yes, this is linear function. Let's write a graph. Where is it linear? We're going to answer the questions in part A. Sorry, that means linear. And this is yes. And what is the slope? The slope is 1 here, and then the y-intercept is -1. G of x, it looks like a rational function, but actually it's not, because if you rewrite g of x, it's really x over 2 minus 1 over 2. So your slope is 1 over 2x, right? Your slope is 1 over 2. So yes, this is a linear function. Slope is 1 over 2. And y-intercept is -1 over 2. So you can draw the linear graph easily. H of x, however, we have x minus 1 and x minus 2 in both of our numerator and denominator. So the variable x is both on the numerator and the denominator. Whenever you see the variable in the denominator, though, you'll see a rational function. So if you have a variable on the numerator and with the same power on the denominator, then it's still a rational function. If you can simplify and make it a linear function, then it could be a linear function. But if you cannot, then high possibility it's a rational function. So for this one, you can plug in one by one, but this is definitely not linear. Slope, because it's not linear, we cannot say what the slope is. And then, so we can say NA. And then y-intercept is when, by definition, when x is equal to 0. So when x is equal to 0, we have 0 minus 1 over 0 minus 2. So we have a y-intercept of 1 over 2, positive 1 over 2. And then we can look at the domain and range. Domain can be 1, but it cannot be 2 because it will make our fraction undefined. So our function will be undefined when x is equal to 2. And so domain is all real numbers except 2. What about our range? Could our range be 1? Possibly, maybe not. If you plug in some numbers for x, will we ever get the same number on the top and the bottom of the fraction? Because that's when we get a 1. So no, we cannot have 1, right? Can we have a 0? We can have a 0 when x is equal to 1. We have 1 minus 1, 0, and then it's still defined because 1 minus 2 is -1. So 0 over -1, it's 0. So yes, it could be 0, but it cannot ever be 1. So what does that mean? Let's look at the graph easily. So I graphed it in Desmos. So our f of x is x minus 1, right? So we start with -1, the y-intercept of -1, and then the slope is 1, so you go up 1 over 1, up 1 over 1, up 1 over 1, and so on. G of x g of x is x minus 1 over 2, but that's when you have negative 1 over 2 as your slope here. And then you have your y-intercept, negative 1 over 2 as y-intercept, and then you have a slope of 1 over 2. So go up 1 over 2, up 1 over 2, so you'll have 2 comma 0.1, yeah, and so on. So this is a linear function. H of x, though, you'll see that it's a rational function where you have a horizontal asymptote at y equals 1, and then a vertical asymptote at x equals 2. So that's where our domain and range cannot be, right? Yeah, so as we looked at in the previous lesson, 4-1, we can see that whatever the restriction of our domain and range are, they define our asymptotes. They give us the equations of our asymptotes. So yes, we have answered part 1. What is the effect on the graph of f when dividing x minus 1 by 2? So if you divide this whole equation by 2, what happens? We're going to basically divide all our range by 2, and that's what happens. Nothing too fancy. So each y value is half of the previous y value. And what happens to the graph of h as x approaches 2? So if you look at the graph as x approaches 2, from the left side, it approaches negative infinity, right? And then from the right side, as x approaches 2, it approaches positive infinity. So depending on the direction that it's coming from, our behavior of the graph changes. So as x approaches 2 from the left, y approaches negative infinity. And as x approaches 2 from the right, the y value approaches positive infinity. Okay. So now, what is the effect on the graph of f of x when dividing x minus 1 by x minus 2? So instead of dividing it by 2, like a constant number, what happens if we divide it by x minus 2? So if we divide it by 2, it's g of x, right? But if we divide f of x by x minus 2 instead, then we get a h of x. So what happens if we divide this function by x minus 2? It becomes a rational function, and it's no longer a linear function, right? Yeah, so that's something that's very different from what we have seen before. So the graph is no longer linear, is what we can say. So we have explored how linear functions and rational functions are related, right? And how they differ. So the essential question that we're going to ask ourselves throughout the lesson is, how can you graph a rational function? Okay, let's look at example 1. Rewrite a rational function to identify asymptotes. Rewrite g of x equals 4x over x minus 3 using long division. How is a quotient related to the reciprocal function f of x equals 1 over x? Sketch the graph. So first of all, we're going to rewrite this using long division. You remember long division, right? So basically, you're going to divide the polynomial or the monomial and the binomial using long division. And so remember, it's your numerator divided by your denominator. So 4x is divided by x minus 3. And how do we divide binomial with a monomial? Well, first of all, you have to look at your first term and try to match it with your term here. So x times what is 4x? 4. Yeah, so 4 times x is 4x, and then we have to multiply the whole binomial. So 4 times negative 3 is negative 2, so we have a constant term to come. So that's 0, and then we have a remainder of negative 12. So that means if we divide 4x divided by x minus 3, we have 4 plus remainder of oh yeah, we're subtracting this, so it's a plus. So we're subtracting this, right? So it's a plus 12. Yeah, so we have a remainder of 12 out of x minus 3. So g of x in other form, so this is the same form. 4x over x minus 3 could also be written as 4 plus 12 over x minus 3. And why do we want to do that? Because we want to compare with our parent function. We want to be able to easily compare it. And it's easier to picture our graph when we just have one variable in a fraction instead of like both, instead of having it the both sides of the fraction, right? Yeah, so we have 4 plus 12 over x minus 3. And so if you remember transformation, we have talked about h and k, but now we have a. So this will be a vertical vertical stretch or compression, right? So in this case, your a is positive 12. So if it's negative, then it's a reflection. It's not even a stretch or compression. Negative is a whole different thing. But if it's greater than 1, it is a stretch. Less than 1, it's a compression. And if it's horizontal stretch or compression, it has to be in front of your x. And it should only change your x, not the whole thing. So again, your g of x, where your transformation of a function from your parent function is defined in the rational function is defined as a over x minus h plus k. So here we have h is equal to 3, positive 3, so we're moving the graph from the parent function to the right 3 units. And then k is positive 4, so we're moving our graph 4 units up. And then a is 12, so we're stretching the graph vertically by a factor of 12. So what is our parent function? Our parent function is f of x equals 1 over x. So whatever your a, h, and k are, you're going to transform your graph according to your parent function, according to the values, right? So from your parent function 1 over x that we have observed in the last lesson, it has an asymptote at x equals 0 and y equals 0, right? And then we have the major points at 1, 1 and negative 1, 1. We're going to shift it up 4 units and write 3 units. So that means our asymptotes are no longer at x equals 0 and y equals 0. Instead, our asymptotes are at y equals positive 4 and x equals positive 3. So yeah, and not only that, we're going to stretch it vertically by a factor of 12. So yeah, so all the points are going to be stretched up. So with the same x, we're going to stretch it up 12 times. So yeah, and that gets a little bit complicated if you do it by hand. So I recommend using technology to graph it accurately, but you can also do it by drawing a table by point, right? You can plug in the numbers in your x and figure out the g of x. But anyway, it's going to be stretched. So if it doesn't require a whole great deal of accuracy, you can just imagine the graph being stretched vertically and sketch it accordingly. Okay, so look at try number 1. You're going to use long division to rewrite each rational function and find the asymptotes of f and sketch the graph. So pause the video, see if you can do it by yourself for parts A and B. Come back when you're ready for answers. Okay, are you ready? So look at part A. If you use long division for part A, you're going to divide 6x by 2x plus 1, right? So you're going to match your first term, 2x, with your 6x. So 2x times 3 is 6x. And then you have to multiply your constant term as well. 3 times 1 is 3. So if you subtract this, you will get 0 minus 3. So your remainder is negative 3. That means you're going to rewrite this in a different form where you have 3, right? 3 is your quotient. Then you have a remainder of negative 3 out of 2x plus 1. Yeah. So this is your new form, and looking at this, you can easily see your a, h, and k, right? So a is negative 3. Identify your values. A is negative 3. H, oh, actually you have another a here, right? So yeah, you have a horizontal compression as well. So this one is also, yeah. So I'm going to write a together. It's negative 3 over 2. Well, actually, if we say the parent function is 1 over 2x plus 1, then we don't have to even worry about that. Yeah, so let's say that our parent function is 1 over 2x plus 1 instead of 1 over x plus 1, and then we can just say a is negative 3, and then we have h is negative 1, right? Because it's plus 1. And then actually we don't know how to graph 1 over 2x plus 1. So I'm going to say a is negative 3 over 2. Okay. And then k is going to be 3. Yeah. So really, if you look at this one by one, you have a vertical stretch by a factor of 3, and the horizontal compression by 1 over 2, and then negative, that is a reflection. So you have a reflection over, so this is with your vertical reflection, so it's over the x-axis, and then you have a translation up 3 units and left 1 unit. Yeah, so how does your graph look like? You have, so starting from our function here, where we had asymptotes here, we're going to move, translate 3 units up and 1 unit left. So our asymptotes are at y equals 3 and x equals negative 1. And then so your original should be like this, right? But it's reflected across x-axis. So that means you have something like this, a graph that's reflected, but it's also vertically stretched by 3 and horizontally compressed by 1/2. So vertically stretched means with the same x you have like a higher, longer graph, and then horizontally compressed by 1/2. That means horizontally you're even, so vertically is stretched even more. So yeah, you can graph something like this. Yeah, so the asymptotes are going to be y equals 3 and x equals -1 for part A. And this would be an approximate sketch of the graph, not an accurate one. And then part B, you do the same thing using long division. You will be able to figure out that this should have a quotient of 1 and a remainder of 6 over x minus 6. So here we can only look at 1a. So a is 6, and then h is +6, k is +1. So we have a vertical stretch by 6, and then horizontal translation 6 units to the right, and then vertical translation 1 unit up. So from our parent function 1/x, 1/x, we're going to imagine, from our parent function 1/x, that looks something like this. We have a translation of 1 unit up, and then 6 units to the right. 1, 2, 3, 4, 5, 6. So we have a horizontal asymptote at y equals 1, and then vertical asymptote at x equals 6. And then our graph should be like this, but then we have a vertical stretch by 6. So then it's steeper, like that. Steeper. Okay. Yeah, so the vertical asymptote is 6, x equals 6, and horizontal asymptote is y equals 1. And then that should be our function in a rewritten format. So check your answers, see if you got it right, and good job if you got it. We'll continue with the next example in the next video.